The strangest thing about the solar system is not that it is flat. It is that we were taught to confuse its flattest part with the whole thing. For most of your life, the solar system has probably lived in your mind as a diagram. The sun at the center. The planets arranged around it like beads on invisible rails. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Sometimes Pluto still appears at the edge, depending on the age of the picture and the patience of the person who made it. The entire structure sits on one clean plane, as if the sun had placed its family on a table and told every world to stay there. That picture is useful. It is also dangerous. It is useful because the planets really do move in nearly the same plane. That is not an artistic trick. It is a memory of birth, a fossil of the rotating disk of gas and dust from which the sun and planets formed. But it is dangerous because it teaches a quiet lie. It makes you feel that the solar system is a flat machine, and that if you flew straight above it or below it, you would quickly escape the real action. You would leave the planets behind, pass through empty space, and be done with our cosmic neighborhood. That is not what would happen. If you rose out of the planetary plane, you would not immediately leave the solar system. You would leave the familiar picture, you would leave the textbook, you would leave the human habit of turning a three-dimensional world into a neat line on a page. But the sun's domain would still surround you. There would be asteroids on tilted orbits, icy worlds far beyond Neptune, scattered bodies moving on steep paths, comets arriving from every direction, and beyond all of it, a vast suspected cloud of frozen remnants extending not just outward, but above and below, wrapping the solar system in a sphere so large that the planets are only a tiny bright knot at its center. The debatable thesis of this journey is simple, and it changes the whole way we should picture our home in space. The solar system is not best understood as a flat disk with a few objects around it. It is a layered three-dimensional structure, a thin planetary sheet at the center, a thicker trans-Neptunian frontier beyond it, a mostly inferred spherical comet reservoir around that, and then a tilted passage through the Milky Way. The flat map is not wrong, but if we let it become our mental model, it hides more of the solar system than it reveals. There is a strong counterargument. The planets contain most of what most people care about. Their orbits are nearly coplanar. Spacecraft navigation often begins with the ecliptic. A flat diagram is not a conspiracy against truth. It is an efficient tool. For teaching the 8 planets, it works beautifully. The problem is not that the diagram exists. The problem is that we forget it is a compression. We mistake the plane of the planets for the shape of the sun's entire gravitational territory. So tonight, the question is not merely what lies above and below the solar system. The deeper question is whether above and below even mean anything once you leave the surface of a planet. And the answer is both humbling and strange. Above the planetary plane is more solar system. Below it is more solar system. Farther out, above and below, become almost meaningless. And on the largest scale, there is no cosmic up, no cosmic down, only reference frames chosen by minds that evolved under gravity. To see why the familiar diagram has power, we have to begin with the reason it is partly true. About 4.6 billion years ago, there was no Earth, no Jupiter, no Mercury rushing around the sun, no Neptune in the dark outer reaches. There was a cold cloud of gas and dust inside the Milky Way. It was mostly hydrogen and helium, but it also carried the ashes of older stars, carbon, oxygen, silicon, iron, and other heavy elements forged in previous generations of stellar death. That cloud was not perfectly still. Nothing real in the universe is perfectly still. It had turbulence, It had local density variations. It had tiny motions inherited from the galaxy around it. At some point, a region of that cloud began to collapse under its own gravity. Perhaps a nearby supernova helped compress it. Perhaps internal turbulence and gravity were enough. The trigger is less important than the consequence. As material fell inward, it heated up, and the collapsing region began to rotate faster. This is conservation of angular momentum. The same principle that makes a figure skater spin faster when pulling their arms close to the body also shapes newborn star systems. A huge cloud with a barely noticeable rotation can become a rapidly spinning disk when gravity pulls it inward. But it does not become a sphere. A collapsing, rotating cloud flattens. Collisions among particles damp motion above and below the plane, while rotation preserves motion around the center. Gas can lose energy by radiating light, but angular momentum cannot simply vanish. Matter falls inward until it reaches a state where its remaining angular momentum is supported by orbital motion. The result is a disk, a rotating sheet of gas and dust surrounding a growing central star. At the center of our disk, the sun ignited. In the disk around it, dust grains stuck to one another, then pebbles, then rocks, then kilometer-sized planetesimals, then protoplanets. The planets were born inside that flattened environment, so they inherited its geometry. This is why Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all orbit the Sun in the same direction and in nearly the same plane. They are not obeying an arbitrary rule. They are preserving the shape of their birthplace. That plane is what astronomers call the ecliptic, defined by Earth's orbit around the Sun. If you could trace Earth's path for 1 year and stretch a flat surface through that orbit, you would have the ecliptic plane. It is the invisible tabletop on which the familiar solar system diagram is drawn. But there is already a subtle problem. The ecliptic is not a physical sheet. It is not a wall. It is not a surface with thickness. It is a reference plane chosen because Earth is where we live. That choice is convenient, but it is not sacred. Mars has its own orbital plane. Jupiter has its own. The invariable plane of the solar system, defined by the total angular momentum of all the planets and smaller bodies, is a slightly different reference. Because Jupiter dominates the angular momentum of the planetary system, that invariable plane sits close to Jupiter's orbit rather than exactly matching Earth's. This matters because the phrase above the solar system already smuggles in an assumption. Above what? Above Earth's orbital plane? Above Jupiter's? Above the invariable plane? Above the Milky Way's disk? Space does not answer until you choose a coordinate system. Still, the ecliptic is a useful starting point. And if we use it, the planetary system really does look impressively flat. Mercury is the most tilted of the 8 major planets, with an orbit inclined about 7 degrees to the ecliptic. Venus is tilted a little more than 3 degrees. Mars is under 2 degrees. Jupiter, Saturn, Uranus, and Neptune all stay close to the same broadsheet. Earth is 0 by definition, because Earth's orbit defines the plane. Those inclinations sound tiny, and compared to the scale of the solar system they are. But tiny angles become enormous distances when the radius is measured in millions or billions of kilometers. Mercury's 7-degree tilt can carry it millions of kilometers above or below the ecliptic. Neptune's much smaller inclination still matters because Neptune is so far from the Sun. The planets do not ride on a painted line. They move within a thin, 3-dimensional band. This is the first correction to the childhood picture. The planetary solar system is not perfectly flat, it is thin. That difference matters. A sheet of paper has thickness. A compact disk has thickness. A galaxy has thickness. The planetary region is extremely flat compared with its width, but it is not mathematically flat. It has depth, and that depth is a record of gravitational history. Why are the tilts not all zero if everything formed in one disk? Because the early solar system was not a calm clockwork. It was crowded, violent, and unstable. Growing planets tugged on one another. Large bodies scattered smaller bodies. The giant planets likely migrated from their original birthplaces, exchanging angular momentum with a massive disk of leftover planetesimals. Jupiter's gravity shaped enormous regions. Neptune's outward migration helped sculpt the Kuiper Belt and capture Pluto-like objects into resonances. The orbits we see today are not the untouched geometry of the original disk. They are the result of billions of years of gravitational negotiation. So the flat diagram contains a real truth, but it is already an edited truth. It shows the surviving order, not the chaos that produced it. It shows the main planets, not the full population. And the moment you add smaller bodies, the solar system begins to rise out of the page. Start with the asteroid belt. It sits between Mars and Jupiter, often drawn as a thin ring of rubble. In popular images, it looks like a crowded band in the same plane as the planets, almost like a debris lane painted between two orbits. In reality, the main asteroid belt is sparse and dynamically diverse. Many asteroids do orbit near the ecliptic, but many have inclinations far larger than the planets. Ceres, the largest object in the asteroid belt and a dwarf planet, is inclined about 10 degrees to the ecliptic. Vesta is tilted about 7 degrees. Pallas, one of the largest asteroids, is tilted about 35 degrees. That is not a minor wobble. Pallas does not politely remain on the planetary tabletop. It cuts through the inner solar system's reference plane like a tilted blade. This is already enough to challenge the diagram. If you include Pallas correctly, the neat flat belt becomes a volume. Objects move above and below the planetary plane by enormous distances. They cross it at nodes, spend long stretches away from it, and carry in their orbits the memory of collisions, resonances, and Jupiter's gravitational stirring. The counterargument is that asteroids are small. They are not planets. Perhaps the solar system is flat where it matters and messy only in the leftover debris. But the leftovers are not trivial. They are the fossil record. They are the fragments that preserve the dynamics of formation and disturbance. If the planets are the architecture, the small bodies are the archaeological evidence. And archaeology is where the hidden history lives. Move farther outward, and the flat picture becomes even less defensible. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies beginning around Neptune's orbit and extending through the outer reaches of the planetary system. It contains Pluto, Haumea, Makemake, Eris, and countless smaller worlds still being discovered. It is not a razor-thin ring. NASA describes it better as a thick disk or donut, a volume of icy remnants left over from the solar system's formation and shaped strongly by Neptune. Pluto itself is the classic warning sign that the simple planetary diagram was hiding something. For decades, Pluto was placed at the end of the planetary line, a small final bead after Neptune. But Pluto's orbit never behaved like the others. It is eccentric, meaning its distance from the Sun changes dramatically during its orbit. It is also inclined about 17 degrees to the ecliptic, more than twice Mercury's inclination. Pluto does not sit at the edge of the plane. It spends much of its long orbit far above or below it, crossing the ecliptic only at 2 points. This was one reason Pluto's planetary status became difficult to defend once more objects were found in the same region. Pluto was not a lonely ninth planet at the orderly edge of the solar system. It was the first famous member of a population. Its weirdness was not random. It was a clue. The Kuiper Belt has different dynamical groups. Some objects are relatively calm, with low inclination, nearly circular orbits that preserve more of the original disk's structure. Others are dynamically hot, with higher inclinations and more eccentric orbits. Resonant objects like Pluto, in its 3-2 resonance with Neptune, orbit in patterns protected from close encounters. Scattered disk objects have been thrown into more elongated and more tilted orbits by interactions with Neptune. Detached objects have closest approaches so far from Neptune that their current orbits are harder to explain by Neptune alone. Each group adds another layer to the real solar system shape. The cold classical Kuiper Belt is closer to the flat picture. The hot classical belt is puffier. The scattered disk is wilder. Detached objects stretch the boundary between the known planetary region and the more mysterious outer cloud. Eris makes the point sharply. It is comparable to Pluto in size and slightly more massive, but its orbit is tilted about 44 degrees to the ecliptic. 44 degrees is not a gentle deviation. It is nearly halfway from the planetary plane toward a perpendicular orbit. Eris lives in a geometry that a flat solar system poster cannot honestly show. If you try to force it into the same diagram as the 8 planets, you flatten the very thing that makes it scientifically interesting. Sedna is different again. It is not as steeply tilted as Eris, but its orbit is enormous. It never comes anywhere near Neptune. Its closest approach is around 76 astronomical units from the Sun, and its farthest distance is hundreds of astronomical units away. Sedna takes roughly 11,000 years to complete one orbit. It moves through a region that is neither the familiar Kuiper Belt nor the classical Oort Cloud, and its existence hints at a deeper reservoir of bodies shaped by early solar system scattering, passing stars, the galactic tide, or perhaps influences we have not fully identified. Then there is Planet 9 or Planet X, depending on the naming preference. This is not a discovered planet. It has not been seen. NASA is careful about this, and we should be too. The hypothesis arose because certain distant trans-Neptunian objects appear to have orbital patterns that might be explained by the gravity of a large, unseen planet far beyond Neptune. But observational bias is a serious counterargument. We discover distant objects where and when our surveys are capable of finding them, not uniformly across the sky. A pattern in the known sample may reflect the true architecture of the outer solar system, or it may partly reflect how we have looked. This is exactly the kind of controversy a science documentary should treat honestly. The tempting claim is that a hidden planet is sculpting the edge of the solar system. The mechanism is plausible. A distant massive body could shepherd or cluster the orbits of smaller objects. The evidence is suggestive. Some extreme trans-Neptunian objects do seem oddly aligned. The limitation is severe. The planet has not been directly observed, the sample size is small, and survey bias can mimic patterns. The consequence is important either way. If Planet 9 exists, the solar system has a major unseen world on a tilted, distant orbit. If it does not, then the distant objects are teaching us that our search methods and dynamical models still miss something about the outer frontier. Either answer breaks the flat diagram, but the outer solar system's strongest evidence against flatness comes from comets. Short-period comets often have origins related to the Kuiper Belt or scattered disk. They tend to stay more connected to the planetary region, though some have strange orbits. Halley's Comet is famous because it returns every 76 years or so, but its orbit is retrograde, meaning it travels around the Sun opposite the direction of the planets. Its inclination is about 162 degrees. In the language of orbital mechanics, that means it is tilted so far that it has flipped over into backward motion. Long-period comets are even more revealing. They can arrive from any direction. Some dive into the inner solar system from above the ecliptic. Some come from below. Some move with the planets. Some move against them. Their orbital inclinations are distributed across the sky in a way that makes no sense if their source is a flat disk. If a reservoir of comets were shaped like the planetary plane, its visitors would mostly arrive near that plane. The fact that long-period comets arrive from all directions suggests a source that surrounds the solar system in all directions. This is the Oort Cloud. The Oort Cloud is one of the strangest parts of astronomy because it is both central to how we describe the solar system and not directly observed in the way the planets are observed. No telescope has imaged a normal Oort Cloud object sitting in place at tens of thousands of astronomical units. The objects are too small, too cold, too dark, and too distant. The cloud is inferred from comet behavior, dynamical modeling, and the logic of solar system formation. It is a powerful inference, but still an inference. That distinction matters. A careless account might say, "We know the Oort Cloud is there exactly as drawn." A careful one says, "The Oort Cloud is the leading explanation for long-period comets, and its broad structure is strongly motivated, but its detailed population, mass, and boundaries remain uncertain." That is not weaker. It is more interesting. It means the outermost solar system is not a solved map. It is a hypothesis supported by messengers that fall inward from the dark. NASA describes the Oort Cloud as the most distant region of the solar system, perhaps extending from thousands of astronomical units to as far as 100,000 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun. Neptune orbits at about 30 astronomical units. The Kuiper Belt's main region extends to roughly 50 astronomical units, while the scattered disk can reach much farther. But the Oort Cloud may extend to tens of thousands or even 100,000 astronomical units, approaching a significant fraction of the distance to the nearest star. This scale destroys ordinary intuition. Voyager 1 crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, in 2012. Voyager 2 crossed in 2018. That sounds like leaving the solar system, and in one sense it is. They entered interstellar space as defined by the solar wind, but they are nowhere near the Oort Cloud's outer edge. NASA notes that Voyager would take about 300 years to reach the inner edge of the Oort Cloud and perhaps tens of thousands of years to pass beyond it. The spacecraft have left the Sun's wind. They have not left the Sun's gravitational frontier. This is one of the most important distinctions in the whole story. The edge of the solar wind is not the same as the edge of the solar system. The heliosphere is the bubble carved by charged particles streaming from the Sun. The Oort Cloud is the distant realm where icy bodies may still orbit the Sun under its gravity. The former is measured in hundreds of astronomical units. The latter may reach 100,000. A spacecraft can enter interstellar plasma while still being deep inside the Sun's extended gravitational family. If you define the solar system by the last planet, it ends at Neptune. If you define it by the Sun's wind, it ends at the heliopause. If you define it by the Sun's long gravitational reach and its comet reservoir, it extends to the Oort Cloud. These are not contradictions. They are different definitions answering different questions, but they matter because it's the childhood diagram usually gives you only the first definition while letting you believe it has shown the whole place. Now imagine traveling straight up from the ecliptic plane, not toward Neptune, not along the planetary disk, but perpendicular to it. At first, you would leave the familiar band of planetary orbits. Earth would shrink behind you. The sun would remain dominant. The paths of the planets would flatten below you into a thin, luminous diagram. But now it would be a diagram you were escaping. You would cross the vertical extent of the asteroid belt. You would pass through an enormous volume in which known bodies are sparse, but not impossible. Some high-inclination asteroids and comets would spend parts of their orbits in regions like this. Farther out, the Kuiper Belt would not be a narrow line, but a thickened distribution. Many of its objects would remain concentrated closer to the ecliptic, but others would occupy steeply tilted paths. You would not see them with your eyes. They are tiny, dark, and separated by vast distances. But dynamically, you would still be moving through a populated region of the solar system. Not crowded, not like an asteroid field fantasy, but not empty in the way the flat diagram suggests. Beyond that, the known objects thin dramatically. There are detached worlds and scattered bodies on long orbits, but the space between them is almost absurdly large. Then, after thousands of astronomical units, you would enter the hypothesized inner Oort Cloud, perhaps more flattened than the outer cloud, perhaps a bridge between the trans-Neptunian populations and the isotropic outer shell. Farther still, you would move into the outer Oort Cloud, where the original plane of the planets has largely lost authority. There, above, and below the ecliptic no longer feel like privileged directions. Oort Cloud objects, if the model is broadly right, are distributed in a thick bubble around the sun. They can orbit at every inclination. Some go over the solar system. Some go under it. Some move in directions that make the old planetary plane irrelevant. The solar system, on its largest scale, is not a plate. It is more like a bubble, with a thin, bright disk buried near its center. This is the strongest answer to the title question. What is above and below the solar system? If by solar system you mean the plane of the planets, then above and below are filled first with sparse, inclined small body populations, and eventually with the Oort Cloud, a vast inferred reservoir of icy remnants surrounding the sun in 3 dimensions. Above the planets is not nothing. Below the planets is not nothing. Above and below are directions through the outer architecture of the sun's domain. But there is a counter-argument here too, and it deserves respect. The Oort Cloud has not been directly observed. Its distances, mass, population, and even the details of its inner and outer components are model-dependent. It is tempting to draw it as a clean spherical shell, but the real structure may be irregular, disturbed by passing stars, the Milky Way's tide, and the sun's birth environment. The Oort Cloud is probably not a perfect snow globe. It is more likely a dynamically sculpted, sparsely populated, evolving reservoir. That limitation does not erase the point. It makes the point sharper. The largest part of our solar system is not a place we have mapped object by object. It is a structure inferred from long-period comets and gravitational logic. Our mental picture should therefore be humbler. The solar system is not a fully drawn territory. It is a known inner disk, surrounded by a partly inferred outer darkness. The formation of that outer darkness is itself a story of violence. The leading idea is that many Oort Cloud objects formed much closer to the sun, in the region of the giant planets, as icy planetesimals left over from planet formation. Jupiter, Saturn, Uranus, and Neptune then scattered them. Some were ejected from the solar system entirely. Some were thrown into distant, elongated orbits, still bound to the Sun but far enough away that the galaxy's gravity and passing stars could reshape them. Over time, those orbits became randomized, producing a spherical distribution. This means the Oort Cloud is not a separate add-on. It is the thrown-away memory of planet formation. It is debris exiled to the borderlands. It is the solar system's attic, filled with bodies that once belonged much closer in and were sent outward by gravitational encounters during the system's chaotic youth. And because the Oort Cloud is so far away, it is fragile. A planet near Earth is tightly bound to the Sun. An Oort Cloud object at 50,000 astronomical units is barely held. The gravitational tug of a passing star, the subtle tide of the Milky Way, or the distant pull of a molecular cloud can alter its orbit. A small nudge can send it inward. Millions of years later, that object may appear in our skies as a long-period comet, brightening as sunlight vaporizes its ices and releases dust into a tail. When you see a long-period comet, you are seeing a message from above and below, not because it necessarily came from a literal top or bottom, but because it came from a region where every direction is possible. Its orbit is a confession that the solar system is not only a disk, it is a volume. Now we have to complicate the word above again. So far, we have defined above and below using the ecliptic plane. That is natural if we are talking about the planets. But the solar system does not float in isolation. It moves inside the Milky Way, and the Milky Way has its own plane, the galactic plane. This is the flattened disk of stars, gas, and dust that makes the Milky Way appear as a glowing band across Earth's night sky. The ecliptic plane and the galactic plane do not match. They are tilted relative to each other by about 60 degrees. That is a large angle. Imagine holding a dinner plate and then leaning it steeply relative to a much larger tabletop. The plate is the solar system's planetary plane. The table is the galaxy's disk. They are not aligned. This means that ecliptic north is not galactic north. If you travel straight above the planetary plane, either you are not traveling straight out of the Milky Way's disk. You are moving through the galactic environment at a steep angle. If you travel straight above the galactic plane, you are not traveling straight above the planets. These are different ups. The Sun sits about 26,000 light-years from the galactic center, in a region often called the Orion Spur, or local arm. It orbits the center of the Milky Way at roughly hundreds of kilometers per second, taking around 200 million years to complete one galactic orbit. But its motion is not just around the center. The Sun also oscillates above and below the Milky Way's midplane over tens of millions of years, pulled back by the gravity of the galactic disk. The entire solar system, including the Oort Cloud, participates in this motion. This galactic bobbing may matter. Some researchers have explored whether passages through denser regions of the galactic plane could perturb the Oort Cloud and increase comet flux into the inner solar system. There have been proposals connecting such cycles to impact rates or even mass extinctions. But this is another place where the science must be careful. The mechanism is plausible. More nearby stars or molecular clouds can disturb distant comet reservoirs. The evidence linking such disturbances to specific extinction patterns on Earth is not settled. Many mass extinctions have complex causes, and periodicity claims are controversial. It is safer to say the Sun's motion through the galaxy can affect the outer solar system, not that it reliably writes Earth's extinction schedule. Still, the larger point holds. Above and below the solar system are not only solar system directions, they are also galactic directions. A coordinate system that feels natural near Earth becomes only one local convention inside a much larger rotating structure. If you travel above the galactic plane, the environment changes. Near the midplane, the galaxy is richer in stars, gas, and dust. Move away from it, and the density of ordinary stars falls. You pass out of the thin disk and into older, thicker stellar populations, then into the halo, a sparse, roughly spherical region containing ancient stars and globular clusters. Beyond the visible halo lies the far larger dark matter halo, whose presence is inferred from gravity rather than light. Farther still, you leave the Milky Way's bound environment and enter intergalactic space, where matter is so thinly spread that even calling it empty feels almost too generous and yet still not quite true. So what is above the solar system if you use the galactic plane? First, the local interstellar medium around the Sun. Then the wider stellar disk, thinning as you rise. Then the halo. Then the dark matter halo. Then intergalactic space. And eventually, depending on your direction, other galaxies, galaxy groups, and the cosmic web. This is why the original question is so revealing. It seems like a simple child's question. What is above the solar system? But it forces us to admit that spatial language is not absolute. Above and below are not properties of the universe. They are properties of a chosen frame of reference. On Earth, up and down feel fundamental because gravity gives them to us every second. Down is the direction your body falls. Up is the direction you lift your eyes. The inner ear, the muscles, the skeleton, the whole nervous system assume this vertical language. But even on Earth, it is local. A person in Bangkok and a person in Buenos Aires have different downs. Both point toward Earth's center. From the perspective of space, there is exists. Their downs are nearly opposite directions. Leave Earth, and the illusion weakens. In orbit, astronauts still experience gravity, but they are in continuous free fall, so up and down become tied to spacecraft orientation rather than a natural floor. Go far from planets and stars, and no single direction demands priority. You can define axes for navigation, but the universe does not care which one you call up. This is not just philosophy. It is part of physics. The laws of nature do not come with an arrow labeled upward. They are rotationally symmetric to a high degree. If you rotate your laboratory in space, the same laws apply. That symmetry is connected to conservation of angular momentum. It is why rotating systems persist, why disks form, why planets orbit, why galaxies spin. But the symmetry also tells us that no direction is fundamentally privileged in empty space. The solar system has structure. It has a plane because it formed from a rotating disk. The Milky Way has a plane because it is a rotating galaxy. The local group has a distribution. The cosmic web has filaments. But these are structures within space, not universal definitions of up and down. A good map must show structure while not pretending its orientation is absolute. That is where the familiar flat solar system diagram fails most deeply. It does not merely compress distances, it implies hierarchy. It suggests the planetary plane is the natural stage and everything above or below is empty backstage. In reality, the planetary plane is a thin central layer inside a larger volume. And that volume itself is tilted inside a galaxy. And that galaxy sits inside a moving group of galaxies. Every scale gives you a new plane, a new orientation, a new possible meaning for above and below. There is another quiet distortion in the diagram: scale. Most solar system pictures exaggerate planet sizes, compress distances, and ignore the enormous emptiness between objects. They must do this, or the picture would be useless. If you draw the sun as a small ball on a page and keep distances to scale, the planets become microscopic specks spread across a room or a building. If you include the Kuiper Belt, you need much more space. If you include the Oort Cloud, the planets become almost impossible to see at all. The Oort Cloud is not just far. It is far and away that makes the planetary solar system look like a central seed. Neptune is about 30 astronomical units from the Sun. The Oort Cloud may extend to 100,000 astronomical units. That is more than 3,000 times Neptune's distance. By diameter and volume, the planets are not the solar system's main spatial feature. They are the inner detail. This is why the phrase, "the edge of the solar system," causes confusion. Neptune is the edge of the major planets. The Kuiper Belt is a frontier of known icy bodies. The heliopause is the edge of the Sun's plasma bubble. The Oort Cloud is the outer gravitational reservoir of comets. The Hill sphere, where the Sun's gravity competes with the galaxy and other stars, is another gravitational boundary. Depending on what you mean by edge, you get different answers. A spacecraft crossing the heliopause has achieved something historic. It has entered interstellar space in the plasma sense, but it has not passed beyond every object that may orbit the Sun. A comet falling from the Oort Cloud belongs dynamically to the solar system, even though it begins its fall from a region where the Sun is only one bright star among many. The more carefully you define the question, the more extraordinary the answer becomes. What is above the planets? Inclined asteroids, comets, and trans-Neptunian objects, mostly sparse and invisible, unless you know where to look. What is above the Kuiper Belt? The scattered and detached populations, increasingly tilted and distant, with some objects on orbits that preserve only a faint memory of the original disk. What is above the heliosphere? Interstellar plasma, cosmic rays, and the local interstellar medium, while the Sun's gravity still reaches farther. What is above the whole gravitational solar system? Eventually, the galactic environment, the Milky Way's disk, halo, and beyond. What is above the universe? The question breaks. The universe is not sitting in a room. There is no outside direction waiting above it. Above is a word we bring with us, not a property the cosmos owes us. This is where the controversy returns. Should we stop using the flat diagram? No, that would be foolish. The flat diagram is one of the most efficient teaching tools in astronomy. For the 8 major planets, it captures a real dynamical fact, common formation in a disk. It helps students see orbital order. It provides a reference for eclipses, transits, zodiacal motion, and planetary alignments. But we should stop treating it as the solar system's portrait. It is more like a floor plan of the central rooms, while the house has towers, basements, courtyards, and a surrounding estate stretching into fog. A floor plan is useful if you know what it excludes. It is misleading if you confuse it with the whole building. The scientifically stronger position is not, the solar system is not flat. That is too simple, because the inner solar system really is extremely flat. The stronger position is that flatness is local and conditional. The planetary region is flat because of disk formation. The asteroid belt is thicker because of dynamical excitation. The Kuiper Belt is a thick disk shaped by Neptune. The scattered disk and detached objects are more three-dimensional because gravitational scattering has lifted and stretched their orbits. The Oort Cloud is roughly spherical because galactic tides and stellar encounters randomize distant orbits. The Milky Way adds another plane tilted to ours. The word above changes meaning at each layer. That is the narrative spine. Flatness is not false, but it is not universal. It is a clue that becomes a trap when overextended. Now picture the journey one final time. You begin on Earth, where down is obvious because the planet pulls you. You launch upward. At first, up is just away from Earth. But as Earth recedes, that definition becomes less useful. You cross the moon's distance, and the Earth-Moon system becomes one moving pair. You pass the orbit of Mars, then the asteroid belt, where the flatness of the planets starts to look like a thin, bright line inside a broader swarm of inclined rubble. You pass Jupiter and Saturn, worlds whose gravity once helped throw countless small bodies outward or eject them entirely. You pass Uranus and Neptune, where the textbook diagram usually ends. But nothing has ended. Beyond Neptune, the Kuiper Belt spreads out like a thickened ring of icy remnants. Pluto circles in its tilted resonance. Haumea, Makemake, Eris, and many smaller bodies move on paths that rise and dive relative to the ecliptic. The sun is still bright, but the cold is deep, and the objects are dark. Farther out, the scattered disk loosens the geometry. Orbits stretch, inclinations climb. Some bodies move in ways that look less like members of a neat family and more like survivors of ancient gravitational violence. Then the known objects become rare. Sedna-like worlds appear as hints of something deeper. The planetary plane has become a memory. You enter the realm where no spacecraft has traveled and no direct census exists. The inner Oort Cloud may begin, perhaps flattened, perhaps complex, perhaps holding far more bodies than we have yet inferred. Then the outer Oort Cloud surrounds you, not as a visible fog, not as a glowing shell, but as an almost impossibly sparse population of icy bodies. You could travel through it for ages and never come near one. Yet statistically, dynamically, it may contain trillions of remnants. At 100,000 astronomical units, the sun is no longer a blazing ruler. It is a bright star with a weak gravitational grip. Nearby stars and the Milky Way itself matter. The boundary of the solar system is no longer a line, but a fading of influence. Go farther, and you are no longer orbiting the sun. You are in interstellar space in the fullest sense, drifting between stellar domains. Then widen the view. The solar system is a tilted seed inside the Milky Way. The ecliptic plane leans sharply relative to the galactic disk. The sun, the planets, the Oort Cloud, and everything gravitationally tied to our star move together around the galactic center and oscillate through the galactic plane. What looked like a flat solar system becomes a small tilted structure embedded in a much larger flat galaxy, which itself is surrounded by a halo that is not flat in the same way. Widen again. The Milky Way and Andromeda dominate the local group. Dwarf galaxies swarm around them. The local group moves within larger structures. The cosmic web stretches in filaments and voids. At these scales, the old question has dissolved entirely. Above relative to what? Below relative to what? There is only direction chosen for the convenience of a map. And yet the question was worth asking precisely because it led us here. It began as a complaint about a textbook image and ended as a lesson in reference frames, formation history, gravitational scattering, comet reservoirs, heliospheric boundaries, galactic structure, and the psychology of orientation. That is the power of a simple question asked carefully. It can break open a hidden architecture. The solar system is not the flat diagram. It is also not merely a sphere. It is a hierarchy of shapes. A rotating disk gave birth to planets. Giant planets disturbed leftover debris. Neptune shaped a thick Kuiper Belt. Distant perturbations lifted objects into detached and scattered orbits. Galactic tides and passing stars helped populate a spherical Oort Cloud. The Milky Way tilted the entire picture into a broader cosmic frame. Each layer has a different geometry because each layer has a different history. So the final answer is not a single object or a single region. What lies above and below the solar system depends on how far you go and what plane you choose. Close in, you find the thin planetary system from a different angle. Farther out, you find inclined asteroids and trans-Neptunian bodies. Farther still, you find the inferred Oort Cloud surrounding the Sun in all directions. Beyond that, you find interstellar space, the galactic disk, the halo, and the vast web of galaxies. And underneath all of it, you find the deeper truth. Up and down are not cosmic facts. They are local habits. There is something unsettling about that. We want the universe to have orientation because our bodies demand it. We want a top and a bottom, a map we can hold, a diagram where the sun sits in the middle, and everything has a place. But the universe is not arranged for our balance. It does not provide a floor. It does not care which way our diagrams face. There is also something freeing about it. If there is no absolute up or down, then looking at the night sky is not really looking upward. It is looking outward from the surface of one small rotating planet. When you stand under the stars, you are not beneath the universe. You are inside it. You are embedded in the planetary plane, inside the sun's extended gravitational cloud, inside the local interstellar medium, inside the Milky Way's tilted disk, inside the local group, inside the cosmic web. There is no ceiling above you, there is only more cosmos. The flat diagram gave us a beginning. It taught us that the planets share a plane because they share an origin. But now we can see the cost of stopping there. The diagram made the solar system feel smaller, cleaner, and more finished than it is. It made us imagine emptiness above and below where there is actually a layered architecture of leftover worlds, inferred comet reservoirs, and shifting reference frames. The true solar system is stranger. It is a thin disk wrapped in a hidden sphere. It is a local plane tilted inside a galactic plane. It is a gravitational family whose outer members may be so distant that they feel almost interstellar, yet still belong to the sun. It is both orderly and chaotic, flat and spherical, mapped and unknown. And perhaps the most honest thing we can say is this: the solar system is not a picture. It is a history. Its shape is the record of how it formed, how it was disturbed, how it scattered its leftovers, and how the galaxy continues to tug at its outermost edge. The planets are the part of that history we can draw easily. The rest is harder. The rest rises above and falls below the page. There is another reason the flat picture survives so easily. From Earth, the sky itself seems to confirm it. The sun, the moon, and the planets all move along roughly the same band of sky, the zodiac. Ancient observers did not need spacecraft to know that something was special about that band. Night after night, season after season, the wandering light stayed near the same celestial road. Mars might drift backward in retrograde motion. Venus might appear as an evening star or a morning star. Jupiter might dominate the night for months, but the planets never roamed randomly across the entire sky. They stayed near the ecliptic. This was one of the first clues that the planetary system is ordered. Before anyone knew what an astronomical unit was, before Newton, before spacecraft, before spectroscopy, people could see that the planets share a plane, because from our perspective, their orbits project onto a narrow strip. The zodiac is the sky's shadow of the solar system's disk. But that shadow is also what makes the hidden structure easy to miss. The objects most visible to human eyes are the ones close to the ecliptic: the sun, the moon, and the bright planets. The fainter objects high above or below the ecliptic were invisible to ancient observers and still hard for modern surveys. Even today, telescope time is finite. If you are searching for new objects beyond Neptune, it often makes sense to search near the ecliptic because many known bodies concentrate there. That practical choice creates a feedback loop. We look where we expect objects to be, we find objects there, and the solar system looks flatter than the full distribution may be. This is not a criticism of astronomers. It is how observation works. Every survey has limits. Every telescope sees part of the sky to a certain depth, at certain times, through certain filters, with certain assumptions. The outer solar system is so distant and faint that selection effects are not a minor nuisance. They are central to the science. A body far from the ecliptic, far from perihelion, small, dark, and moving slowly, can remain unnoticed for decades or centuries. The undiscovered population is not likely to be a simple, scaled-up version of the discovered one. That is why debates about the distant solar system are so delicate. When a group of known extreme trans-Neptunian objects appears clustered, is that a dynamical signature of an unseen planet, or a scar left by the way we searched? When high-inclination objects are rare in the catalog, are they rare in reality? Or are they hiding in parts of the sky where surveys were weaker? When we sketch the Oort Cloud, are we drawing the true outer boundary of the Sun's family, or the best inference allowed by comets that survived enough disturbances to reach us? A stronger documentary does not pretend those questions are settled. It uses them. Because the most interesting version of this story is not that the solar system is secretly spherical, and everyone was wrong. The interesting version is that the solar system changes its apparent shape depending on which population you measure and how complete your measurements are. The planets say disk. The asteroids say thickened disk. The Kuiper Belt says donut. The scattered disk says disturbed volume. The long-period comets say sphere. The Oort Cloud says inferred envelope. No single shape wins everywhere. The solar system is not one geometry. It is a sequence of geometries. This is why above is not just a direction. It is a diagnostic. Ask what lies above the ecliptic at 1 astronomical unit, and the answer is mostly empty interplanetary space, crossed by spacecraft trajectories, dust particles, and the occasional high-inclination object. Ask the same question at 3 astronomical units, and asteroids begin to matter. Ask at 40 astronomical units, and trans-Neptunian objects enter the story. Ask at 500 astronomical units, and detached and scattered populations become relevant. Ask at 50,000 astronomical units, and the Oort Cloud dominates the concept of solar system architecture. The answer changes with distance, because the solar system is stratified. Even the dust has a story to tell. The inner solar system is filled with a faint cloud of interplanetary dust, much of it produced by asteroid collisions and comet activity. From Earth, this dust creates the zodiacal light, a faint triangular glow visible under dark skies before dawn or after dusk. It lies along the ecliptic, because the dust cloud is broadly associated with the plane of the planets. That glow is one of the few ways ordinary observers can see the flatness of the inner solar system directly. It is the disk made visible not by planets, but by dust reflecting sunlight. Yet dust, too, has vertical thickness. Tiny grains are pushed by radiation pressure, altered by the solar wind, and disturbed by planetary gravity. Some come from comets on tilted orbits. Some spiral slowly inward under pointing Robertson drag, losing orbital energy as they absorb and re-emit sunlight. The dust cloud is not a perfect sheet, it is a soft, dynamic structure. It reminds us that even the flattest parts of the solar system are made of populations, not lines. Now consider spacecraft. Human machines have already tested the idea of above and below in a practical way. Most planetary missions travel near the ecliptic because that is where the planets are. If you want to visit Mars, Jupiter, Saturn, or Neptune, you do not launch straight out of the plane. You stay close to the shared road. The geometry of exploration reinforces the same mental picture as the textbook diagram. But not every mission stays there. The Ulysses spacecraft, launched in 1990, used Jupiter's gravity to swing into a high-inclination orbit over the Sun's poles. It was designed precisely because the ecliptic view is incomplete. From Earth and most spacecraft, we see the Sun mostly from near its equatorial region. Ulysses gave scientists a way to study the solar wind and heliosphere from higher solar latitudes. In other words, even the Sun has an above and below when we choose its equator as a reference, and for decades that dimension was poorly sampled. This is a recurring theme. We know the plane best because we live in it and explore from it. The vertical dimension is harder. It requires special trajectories, different survey strategies, and more patience. The flat map is partly a diagram of nature and partly a diagram of our access. The heliosphere adds another layer of complexity. It is often imagined as a round bubble, the Sun blowing a sphere of charged particles into the surrounding interstellar medium. But the real heliosphere is shaped by the Sun's motion through the galaxy, the interstellar magnetic field, solar activity, and the pressure of cosmic rays. It is not a perfect sphere centered on the Sun like a soap bubble in still air. It is a dynamic boundary, compressed and stretched, changing with solar cycles and external conditions. That matters for the above and below question, because the heliosphere does not align neatly with the ecliptic in a simple textbook way. The solar equator, the ecliptic, and the local interstellar magnetic environment are all different reference frames. If you travel above the ecliptic, you do not necessarily travel above the heliosphere in the sense that matters to plasma physics. The boundary you cross depends on the direction of the interstellar flow, the solar wind, and magnetic fields. Space is not organized around our diagrams. Voyager 1 and Voyager 2 made this distinction real. They crossed the heliopause at different times, in different directions, through different parts of a boundary that is neither smooth nor perfectly symmetric. Their crossings were historic because they gave us direct measurements of the transition from solar plasma to interstellar plasma, but they also exposed how misleading the phrase "left the solar system" can be. If the solar system means the heliosphere, yes, they crossed a boundary. If it means the gravitational family of the Sun, they are still near the center of a much larger structure. Imagine explaining this to someone using only the old flat diagram. You would point beyond Neptune and say, Voyager is out there. Then you would have to zoom out so far that Neptune's orbit shrinks almost to nothing. Then you would have to draw the heliopause. Then zoom out again by orders of magnitude to draw the Oort Cloud. At that scale, the planets are not visible. The familiar diagram has not merely lost detail, it has changed category. It was never designed to contain the whole truth. This is why scale and shape cannot be separated. The solar system appears flat when you focus on the planets. It becomes a volume when you include the small bodies. It becomes a sphere when you include the Oort Cloud. It becomes a tilted moving system when you include the galaxy. It becomes a set of relative coordinates when you include the broader universe. Let us make the claim more concrete. Suppose you could build a probe capable of traveling 1 astronomical unit straight above the ecliptic. From there, the planetary orbits would look like thin ellipses below you. The sun would still dominate the view. Earth would be a small, bright dot moving along its path. You would not have left the planetary region so much as stepped out of the plane to view it from a new angle. The solar system would look more obviously flat from there, because perspective would reveal the thinness of the orbits. Now travel 10 astronomical units above the ecliptic. The plane of the planets becomes a narrower band. The sun is still bright, but the vastness becomes more obvious. You are far from the usual traffic of planets, but not outside the sun's realm. Objects with inclined orbits may still cross such heights. Comets can pass through from any direction. Dust is thinner, gravity quieter, the geometry less tied to the familiar plane. At 100 astronomical units above the ecliptic, you are beyond the main planets and near the scale of the heliopause in some directions. The sun is still the central gravitational body, but its light has weakened enormously. The planetary plane is now a tiny structure, a bright inner system embedded in darkness. You may be in interstellar plasma, depending on direction and solar conditions, while still being nowhere near the Oort Cloud. At 1,000 astronomical units, the inner solar system is a small point around the sun. Even Neptune's orbit is tiny. You are approaching the region where some models place the inner edge of the main Oort Cloud, though definitions vary. The ecliptic plane no longer controls the view. A tilted trans-Neptunian object might have an orbit reaching such distances, but the known population becomes sparse and uncertain. At 10,000 astronomical units, the sun is still the object you are gravitationally tied to if you are bound. But the galaxy has become a serious participant. The Milky Way's tide is no longer an abstract background. Passing stars matter. A small change in velocity can decide whether an icy body remains part of the solar system, falls inward as a comet, or is lost to interstellar space. Here the solar system is not a mechanical model of nested planets. It is a loose gravitational ecology. At 100,000 astronomical units, the difference between above and sideways is almost gone. You are in the outer borderland where the sun's pull competes with the surrounding galaxy and neighboring stars. The ecliptic is a historical fact, not a governing plane. The solar system's outer shape is defined less by the disk of its birth than by the gravitational environment of the Milky Way. This vertical journey shows the central mechanism. Gravity formed the solar system in a disk, but scattering and weak binding made the outskirts three-dimensional. The inner system remembers the disk strongly because objects there are tightly bound and dynamically organized. The outer system remembers the disk weakly because objects there have been thrown outward and then reworked by external forces. Flatness fades with distance. There is also a subtle philosophical consequence. When people ask what is above the solar system, they often imagine an empty escape route, a direction that leads away from the solar system faster than traveling along the plane. But if the Oort Cloud surrounds the sun roughly in all directions, then straight above is not an exit shortcut. It is simply another path through the sun's outer domain. The solar system does not end quickly above the planets. It extends upward into the same vastness as outward. This changes the emotional scale of home. We usually think of our solar system as the planets, because those are the worlds with names and images. But by spatial extent, the named planets occupy almost nothing. The real volume of the solar system is dark, cold, sparse, and mostly unknown. We live in a bright inner room surrounded by a vast unlit estate. The estate is part of home, even if we rarely mention it. And yet, we must not overstate it. The Oort Cloud is not full in the way a cloud in Earth's sky is full. If you were there, you would not see a mist of icy bodies. The average separation between objects would likely be enormous. The term cloud can mislead just as the term disk can mislead. It is a cloud statistically, dynamically, not visually. It is a population spread through space so thinly that human intuition fails. The solar system's largest structure may also be one of its emptiest. That emptiness is part of the beauty. The outer solar system is not a crowded frontier, but a near vacuum carrying a memory of formation. A few icy bodies per staggering volume. A faint gravitational allegiance to the sun. An occasional comet dislodged after millions of quiet years. It is not dramatic in ordinary time. It is dramatic because it shows how far the sun's story reaches. This is also why future surveys matter. Instruments that scan wider, deeper regions of sky will keep changing the outer solar system's map. New trans-Neptunian objects can alter the debate about Planet 9. New high-inclination bodies can reveal whether our current catalog is biased toward the ecliptic. More discoveries of Sedna-like objects can test whether there is a distinct inner Oort population. Each new body is not just a point in a catalog. It is a clue to the solar system's three-dimensional architecture. The history of astronomy warns us against thinking the map is finished. Pluto was found in 1930 and looked unique for decades. The Kuiper Belt was not observationally confirmed until 1992. Eris helped force a redefinition of planets in the 2000s. The outer solar system has repeatedly turned out to be richer than the previous generation's diagram. There is no reason to assume the next generation will not revise the picture again. That uncertainty should not weaken the documentary thesis. It strengthens it. A flat diagram looks finished. A three-dimensional map remains open. The known solar system is not merely a set of planets. It is an evolving scientific frontier. And much of that frontier lies outside the plane, where our eyes and surveys first learn to look. There is a final scientific caution about saying there is no up or down. In local gravitational fields, up and down are real enough for physics and survival. On Earth, down is not an illusion. It is the direction of gravitational acceleration and the gradient of gravitational potential near your body. On a spacecraft under thrust, the direction opposite acceleration can function as an artificial down. Near a rotating station, centrifugal effects could define a floor. Direction is not meaningless everywhere. It is contextual. The mistake is not using up and down. The mistake is treating them as universal. The universe permits local verticals. It does not supply a global one. Earth gives you a down. The ecliptic gives astronomers a convenient north and south. The Milky Way gives a galactic latitude. The cosmic microwave background gives a rest frame in which its radiation looks most uniform. Each system has a definition. None is the final orientation of reality. That is the careful version of the idea. Not up and down do not exist, because locally they do. Rather, there is no absolute up or down that applies everywhere in the cosmos. Above the solar system means above a chosen plane, and the meaning changes when the plane changes. Once you understand that, the old diagram becomes less like a lie and more like a first language. It taught us the grammar of planetary order, but now we can learn the larger language. Inclination, resonance, scattering, heliopause, Oort Cloud, galactic tide, reference frame, halo. The solar system is not less beautiful because the simple picture fails. It is more beautiful because the simple picture was only the beginning. There is one more reason this subject deserves a stronger treatment than the usual explanation. The question of what lies above and below the solar system is also a question about how civilization builds images of reality. We do not experience the solar system directly. We inherit it through diagrams, animations, classroom models, planetarium shows, and short videos that must simplify or fail to communicate at all. Every model leaves something out. The danger begins when the model becomes invisible, when we forget that we are looking through a simplification. A classroom model with planets on wires can teach orbital order. It cannot teach scale. A poster can teach the sequence of planets. It cannot teach inclination. A top-down animation can teach revolution. It cannot teach the vertical thickness of small body populations. A flat image can teach that the solar system formed from a disk. It cannot teach that the disk is only one chapter of the story. This is why the best counter-argument to the flat map critique is also the best reason to improve the map. Simplification is necessary. No one can introduce a child to planetary science by beginning with Oort cloud anisotropy, survey bias, invariable planes, and galactic tides. The simple picture is a doorway, but a doorway should lead somewhere. If the observer never learns that the diagram has depth missing from it, the doorway becomes a wall. The better question is not whether the flat diagram is wrong. The better question is when it becomes wrong. For Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, it is mostly right as a first-order view. For Ceres and Vesta, it begins to lose precision. For Pallas, it is visibly inadequate. For Pluto, it becomes misleading. For Eris, it fails almost completely. For long-period comets, it is the wrong geometry. For the Oort cloud, it is not merely incomplete, it is conceptually inappropriate. You cannot understand a spherical comet reservoir by flattening it into a line. That gradual failure is important because it teaches scientific thinking. Models are not true or false in a simple way. They have domains. Inside their domain, they can be powerful. Outside it, they can become traps. The flat solar system map is valid inside the domain of planetary orbits. It is not valid as a complete description of the sun's gravitational system. A mature understanding of science means knowing not only what a model explains, but where it stops explaining. This is the same lesson that appears across physics. Newton's gravity works beautifully for planets, spacecraft, and everyday motion, until you need the precision of general relativity near strong gravitational fields or over long times. The Bohr model helps people imagine atoms until its little planet orbits mislead them about quantum mechanics. The flat solar system diagram helps us understand common formation in a disk until it erases the outer three-dimensional architecture. Science advances not by throwing away every old picture, but by learning the limits of each picture. In that sense, the solar system is a perfect training ground for humility. We know its inner planets well enough to land machines on them. We can predict eclipses centuries into the future. We can thread spacecraft through gravitational assists with astonishing precision. And yet the outer edge of the same system remains partly inferred. We have flown past Pluto and Arrokoth, but no spacecraft has entered the Kuiper Belt as a surveyor in the full sense. We have crossed the heliopause, but not reached the Oort cloud. We have seen comets fall inward, but not watched their quiet ancestors in their distant reservoir. Our confidence and ignorance coexist. That coexistence is the honest emotional core of this topic. The solar system is familiar enough to feel like home, but large enough to defeat almost every home-like intuition. It has an address, a history, and a shape, but the shape changes with scale. It has an edge unless you ask which edge. It has an up and down unless you ask relative to what. It is mapped unless you mean the object's too faint and distant to detect. It is orderly unless you look at the survivors of its ancient chaos. This is why a journey above the solar system is really a journey through layers of certainty. The planetary plane is highly certain. We measure those orbits with extraordinary precision. The Kuiper Belt is observed, but incompletely sampled. The scattered disk is known, but biased toward objects that come close enough and bright enough to be found. Detached objects are few, and every new discovery can shift the debate. The Oort Cloud is widely accepted as the source of long-period comets, but its exact structure is not directly mapped. Planet 9 is a serious hypothesis to some researchers and unnecessary to others. The galactic context is real, but proposed biological consequences of galactic plane crossings remain speculative. Each layer requires a different level of confidence. A good voiceover should let the public feel those changing confidence levels. It should not flatten uncertainty any more than it flattens space. It should say, "This is measured. This is inferred. This is debated. This is unknown." That rhythm does not weaken the story. It makes the story trustworthy. And in a topic built around the failure of a simplified picture, trust matters. Now imagine a future map of the solar system, one not printed on a page, but built in 3 dimensions. You could stand near the sun and see the planetary orbits as luminous rings. You could tilt the view sideways and see how thin the planetary plane really is. Then you could switch on asteroids, and the sheet would thicken. Switch on the Kuiper Belt, and a donut of icy orbits would appear. Add the scattered disk, and long tilted paths would stretch outward like loops of wire thrown into the dark. Add detached objects, and the scale would expand brutally. Add the Oort Cloud, and the planets would vanish into a central speck, while a vast spherical haze surrounded everything. Then you could overlay the heliosphere, a boundary not of solid matter, but of plasma pressure. You could see that it is tiny compared with the Oort Cloud, yet enormous compared with the planets. You could rotate the entire model into the Milky Way's frame and watch the ecliptic plane tilt steeply against the galactic disk. You could animate the sun's orbit around the galaxy and its vertical oscillation through the midplane. You could watch passing stars and the galactic tide nudge outer comets. At that point, the old flat poster would not look false. It would look like the first frame of a much larger film. That larger film is what we should carry in our minds. Not because every detail is settled, but because it is closer to the universe we inhabit. We live in a 3-dimensional gravitational system. We live in a moving disk inside another moving disk. We live inside a local bubble of interstellar gas, surrounded by a galaxy whose own structure has thickness, warp, and halo. We live on a planet whose sense of vertical is useful for walking, not for understanding the cosmos. The final correction is emotional rather than technical. When you ask what is above the solar system, the instinct is to imagine emptiness, but the deeper answer is not empty. It is full of scale, history, and perspective. It is full of objects too faint to see, boundaries that depend on definitions, comet paths that arrive like messages from the dark, and reference frames that reveal the limits of human language. Above and below are not doors out of the solar system. They are directions into its hidden dimensions. And there is one final practical reason to care. The hidden vertical structure is not merely an abstract curiosity. It affects what we can discover, where we search, and what risks or opportunities we notice. Comets that arrive from high inclinations can approach the inner solar system from directions surveys are less accustomed to watching. Distant objects far from the ecliptic can test whether our outer solar system models are biased. Future interstellar probes will not simply move through a flat diagram. They will cross plasma boundaries, dust environments, and gravitational regions whose shapes depend on direction. Navigation, observation, and theory all become richer when the solar system is treated as a volume rather than a line. The same is true for public imagination. A flat map makes the solar system feel finished. A three-dimensional map makes it feel alive. It reminds us that Neptune is not the end. Pluto is not just a demoted dot, and comets are not random visitors from nowhere. They are part of a structure so large that its outer edge approaches the territory of other stars. It reminds us that the Sun's family is not just the worlds bright enough or famous enough to name, but also the dark bodies we infer from the way they occasionally fall inward after eons of silence. This is why the honest answer has to remain slightly uncomfortable. We can say what lies above and below the planetary plane, but only by admitting that the question is human-shaped. We can describe the Oort Cloud, but only by admitting that we have not directly mapped it. We can talk about Planet 9, but only by admitting it may not exist. We can draw the heliosphere, but only by admitting it breathes and deforms. We can locate the solar system in the Milky Way, but only by admitting that the galaxy gives us another tilted frame, not an absolute truth. The reward for that discomfort is a better universe. Not simpler, better. A universe where the first diagram was not the answer, but the invitation. There is no shame in beginning with the simple map. Every science begins with a sketch. The danger is staying there after the sketch has done its job. The solar system invites us to grow past the childhood picture, not by discarding it, but by placing it inside a deeper one. The planets are a thin musical line. The asteroids add dissonance. The Kuiper Belt widens the chord. The Oort Cloud turns the chord into a sphere. The galaxy tilts the whole composition into a larger movement. And somewhere inside that movement, on one small world, we learn to ask which way was up. The answer is not a direction, it is a lesson in scale. That is why this question matters more than it first appears. It is not only about what sits above a plane. It is about whether we are willing to let a familiar picture become strange again. The solar system has always been larger than the image we inherited. The moment we restore its missing dimension, our home stops being a diagram and becomes a place, an actual home. So the next time you see the familiar line of planets, do not reject it. Read it correctly. It is not the solar system. It is the solar system's central sentence. Beyond that sentence is a much longer book, written in tilted orbits, comet paths, invisible clouds, and reference frames that dissolve when you push them too far. If you could fly straight out of the ecliptic tonight, you would not find a blank above. You would find the failure of your old map. You would find that the solar system has depth. You would find that the word above slowly loses its authority, and eventually, after crossing distances so large that even light needs years to measure them, you would understand the thing the diagram never told you. The solar system was never just a flat arrangement of planets. It was a three-dimensional home all along, and we were never looking up at it from below. We were inside it, looking out. The useful conclusion is not that the mystery becomes smaller. It becomes better framed. A strong scientific story does not need to pretend that every uncertainty is a revelation. It only needs to show where the pressure comes from, what mechanism could answer it, and where the present evidence still refuses to close the door.